you have any idea how many times computer capabilities increased from the 1940s to the present day? Take a guess. Hundreds of times? Thousands? Well, actually, they've increased by hundreds of trillions of times. And this is just the beginning. Many scientists predict that computer capabilities will increase by millions of times in the coming decades. This means we'll be able to create virtual worlds so complex that their characters will be as complex as we are. In other words, they would have consciousness, just like us. But they wouldn't know they are living in a simulation. Wait a minute. What if? What if we are those very characters? Sounds preposterous, doesn't it? But does it really? For instance, Elon Musk firmly believes that we are living in a simulation and often talks about it in interviews. He literally said, "There's a 1,000,000,000 to 1 chance we're living in base reality." But Musk is not alone here. More and more people with academic degrees are saying the same thing. Today, we'll find out the odds of us really living in a simulation, what evidence points to this, and explore the implications of this knowledge if in fact this is true. Do we live in a simulation? Please give us a thumbs up. Your like helps YouTube algorithms understand that this content is worth watching. To understand the first piece of evidence, we need to know the basic principles of how computer games, simulations, and metaverses work. We move our character within a game, and the game engine quickly generates the entire surrounding in front of us. City streets, cars, other people in the game. All of this appears only at the moment when the character is looking at it. There is simply nothing outside of this field of view. Absolutely nothing, not even emptiness. Or let's say you're wearing VR glasses. When you look straight ahead, everything behind you doesn't load, and it doesn't become visible or real until you turn your head. Yet, whatever has been in front of you instantly vanishes as soon as you turn around. But then, when you take off the VR headset and look at the real world, everything unfolds exactly the same. So the question is, how do we know that something exists if we're not directly looking at it? What if the universe really uses the same principle, showing us whatever we observe? This is where we come to the evidence suggesting that our world is virtual. The first piece of evidence. You might be familiar with the observer effect. This fascinating phenomenon became recognized as a result of Young's experiment, also known as the double-slit experiment. YouTube is full of detailed explanations and demonstrations of this experiment, all because it is the most famous experiment in the history of physics, which has been repeated the most number of times, with the most shocking results and the most accurate measurements ever. In a nutshell, the experiment boils down to the following. Light behaves in a very strange way when its structure is scrutinized. As we know, light is electromagnetic waves. However, when you start measuring the properties of a specific light beam with the greatest precision, it no longer behaves as a wave, but as a stream of particles. There is no contradiction or error here, merely a paradox scientists encounter when delving into the subtle levels of matter. To put it simply, when unmeasured, light acts as a wave, but when measured, it acts as particles. This might sound unconvincing if you talk about such semi-abstract things, but in fact, this is quite a startling paradox. It's like saying that when you look at a cup of coffee, it's a cup of coffee, but when you don't, it's the sound of the sea. In other words, if you observe light with high precision, it abruptly changes its basic characteristics, as if it knows it's being observed. Once again, this explanation is very simplified and doesn't describe all the amazing effects discovered during the experiment. The Young experiment has been replicated by various scientists and enthusiasts an unimaginable number of times, each time confirming that everything indeed works in this unfathomable way. One might ask, what difference does it make what happens in this quantum world? However, similar effects were observed not only with light, but also with electrons and individual atoms, the basic building blocks of all matter that surrounds us. This train of thought takes us to a staggering conclusion. Does this mean that if I'm not observing the moon, it doesn't exist at that moment? Well, it turns out so. Although, of course, everything is much more complex than that. We simplify it just to make it easier for you to understand the next argument. The second piece of evidence. Now, let's consider another peculiar setting of our world that blatantly stands out: the speed of light. It is constant, unchangeable, and cannot be exceeded under any circumstances. Doesn't it instill a sense of doom, or even a little unfair? You can't help but say, what the hell? But let's look at the speed of light from a different perspective. For instance, let's consider the clock speed of your laptop or smartphone processor. It's a fixed number of gigahertz, clearly stated in the technical specifications. You can't exceed it. It's simply impossible. Somehow, we calmly accept this as a given. How else could it be, after all? Yet, the limitation of the speed of light sparks outrage in many of us. So, what if the unalterable speed of light merely reflects the maximum computing power of the mysterious machinery controlled by even more mysterious architects of our world? A world that might actually be a simulation. The fixed limit of 300,000 kilometers per second does seem peculiar. Let's see how it works. As an object's speed increases, its time slows down. This has been proven by numerous experiments. We know this for certain. Time completely stops for any object moving at a speed of 300,000 kilometers per second. This means that if you had a spaceship capable of accelerating to the speed of light, and you decided to fly to a distant galaxy 3 billion light years away, you'd get there in an instant. But it would only be an instant for you, as the time on the ship would completely stop during the flight. However, back on Earth, 3 billion years would have passed. So photons of light indeed move at a speed of 300,000 kilometers per second, and therefore their time stands still. This makes it impossible to go any faster, because to increase the speed, you'd have to slow down time even more, which is already at zero. This raises a question. Why is it that speed slows down time in our universe? Why are space and time interconnected? Why on earth does our reality have such a strange limitation? Why should it be there at all? It seems highly unusual for a physical world, but perfectly reasonable for a virtual one. If we live in a computer simulation, then the speed of light might be a product of information processing. Information. Please bear this word in mind. The speed of light limitation is often described not only as something cannot move faster than light, but as information cannot be transmitted faster than the speed of light. Don't you see this striking analogy with the world of information technology? It seems that the principle of information exchange in our universe resembles that within our computers. The third piece of evidence: discreteness of space and time. In modern physics, there is a measurement system called the Planck Unit. According to this system, the smallest measurable unit of space is 1.6 times 10 to the power of minus 35 meters. It's impossible to measure a length smaller than this unit. What's more, this is the minimum length that can possibly exist. There is simply nothing smaller than this in the universe. Even empty space is not continuous, but consists of such infinitesimally small chunks. Moreover, Segments shorter than this cannot exist in our physical universe. Otherwise, all known physical laws would be violated. Doesn't this ring a bell? It's literally like pixels on a computer screen. The image on the screen can't be smaller than 1 pixel. But the story doesn't end here. This pixelated nature of the universe has further implications, and it's truly breathtaking to realize them. Bear with us for a bit. Pixels on the screen exist constantly, whether light is projected on them or not. Similarly, cells of space the size of 1 Planck length constantly exist in the physical universe, and they do so regardless of whether there's something in them at a specific moment. You probably know that the screen doesn't continuously emit light, but refreshes at a certain frequency. The most common is 60 Hz, 1/60th of a second. The image on the screen changes during this brief period. Similarly, in the physical universe, there's a minimum measurable time akin to the minimal length known as Planck time. This amount is also infinitesimally small, 5.4 times 10 to the power of minus 44 seconds. As light travels through space, it sequentially occupies adjacent cells of space, one after another. The movement of a quantum photon of light between neighboring cells occurs instantaneously in a leap, since a quantum is indivisible and cannot travel in parts. The time light spends in one cell equals 1 Planck unit of time. The cells of space are stationary, so while light occupies a cell, it remains stationary too. Taking into account the size of the cell and Planck time, you can calculate the maximum speed of light. This means that the speed of light is determined by the size of the cell and the minimum unit of time. As a photon jumps from one cell to another, staying in them for only 1 Planck unit of time, it reaches the maximum speed of 300,000 kilometers per second. Planck time suggests that the universe exists for this brief duration. Then it seems to completely vanish, only to rematerialize during the next Planck unit of time. The universe flickers, just like the image on a computer screen. The sole difference is that a computer screen refreshes 60 times per second, while the universe refreshes 5.4 times 10 to the power of minus 44 times per second. Our senses can't detect such a high refresh rate of the universe, and so we perceive the world as continuously existing, just like we don't notice the flicker on the computer screen. Finally, here is the currently strongest 4th piece of evidence that we live in a virtuality. This is quantum entanglement. To understand its essence, we need to look at it from afar again. Imagine a microparticle, such as a photon of light, flying through space. Each such particle has a characteristic: spin. Very roughly, it can be compared to the spin direction. In fact, the photon does not rotate at all, but for the sake of understanding, let's assume such an analogy. So when all physicists on the planet puzzled over the reasons of such mystical results of Jung's experiment, Einstein, who did not like this mysticism at all, proposed an interesting experiment, which would have to disprove the observer effect. Its essence is as follows. If a caesium atom emits 2 photons in different directions, their states get interrelated because of the law of conservation of momentum. This is called quantum entanglement, and it's determined by spin. If one of the entangled photons spins from top to bottom, then the second photon should spin from bottom to top, i.e., have the opposite spin. It's unambiguous, and there are no exceptions. It's like a pair of gloves. If one of them is right, then the other is definitely left, sure as hell. And experiments confirmed it at first. Indirectly, it turned out that the entangled photons already contain information about what spin they possess. But Jung's experiment, which was repeated, checked, and rechecked in Einstein's time for countless times, proved that the entangled photons just have no idea what spin they should have, until they're measured. It seemed that Einstein was right once again, and there was something wrong with quantum physics. But 17 years after Einstein's death, another scientist, John Bell, did something impossible. He came up with one incredibly cunning and very complicated experiment that would prove or disprove the theory that elementary particles have information about their spin embedded in them in advance. The experiment results were astonishing. They clearly and explicitly showed that before observation, particles really know nothing about how they will spin when their state is measured. Simply put, before the measurement, they just don't have any spin. This property only appears after the measurement. The photon randomly chooses its spin, and that's why the comparison to gloves is inappropriate. Okay, so what? It appears that entangled particles can easily transmit information to each other much faster than the speed of light. If you spread the entangled photons even to different ends of the universe, measure one of them, and find out that it has an upspin, then the second one will have a downspin instantly. Physicists were totally stunned by this. No one could understand how such a thing was even possible. In 2008, a group of Swiss researchers from the University of Geneva set out to determine how quickly the second entangled particle learns that the first has been measured. They scattered two entangled photons 18 kilometers apart, measured one particle, and began to record the rate at which the second particle would react to it. The scientists had the technology to detect a delay of 100,000 times the speed of light, but no delay was detected. That meant that entangled photons could communicate with each other at least 100,000 times faster than the speed of light, and most likely instantaneously. Although Einstein was wrong about entangled photons, he may still have been right about one thing. That's when he said that instantaneous communication in the physical world was impossible. Well, maybe it is impossible in the real physical world. What he didn't realize is that we are probably living in a digital virtual reality. And that's where instantaneous communication is very easy to explain from this point of view. Let's say photons are some sort of equivalent of pixels on a screen. When two pixel photons become entangled, their programs combine to jointly manage the 2 points. If one program is responsible for the top spin and the other for the bottom spin, their joining will be responsible for both pixels, wherever they are. When one entangled particle is measured, its program randomly selects one of its spins, and the program of the second entangled particle responds accordingly by assigning it the opposite spin. This code ignores distance because the processor doesn't have to literally walk to a pixel on the screen and ask it to spin upside down, even if the screen is as big as the universe itself. And by the way, maybe the fact that we're all part of a computer simulation explains the Fermi paradox. We covered the Fermi paradox in another video. Check it out. The link is in the upper right corner. Could it be that we still haven't encountered other life forms simply because they are just not programmed into our simulation? However, this same assumption might suggest that they could be discovered at any moment. Who knows what the universe's game designers have programmed there after all? There's another astonishing phenomenon, this time not in the realm of physics, but society. In 2009, a self-proclaimed paranormal consultant, Fiona Broom, stumbled upon a rather peculiar fact. Contrary to her belief, The world-renowned human rights advocate Nelson Mandela had not died in prison during the 1980s. Instead, he had been released in 1990 and even managed to serve as the president of South Africa for several years. One might dismiss these assertions as mere fantasies of a paranormal consultant. However, Fiona Broome was so convinced that she distinctly remembered newspaper headlines announcing Mandela's death that she decided to conduct a full investigation. The results were mind-blowing. A surprising number of people, entirely unconnected to each other, also held the same belief. Many even claimed to remember Nelson Mandela's daughter's eulogy at his imagined funeral. The phenomenon took on a global scale when the politician eventually died in 2013. At that time, thousands of people around the world were taken aback by the news. Like Broome, they were under the impression that Mandela had died in prison during the 1980s. Fiona Broome named this phenomenon the Mandela Effect. Yet, this was just the beginning of this very peculiar social phenomenon. With the rise of social networks, it quickly became evident that thousands of people from around the globe firmly believe in certain facts that aren't actually true, or their beliefs slightly, yet distinctively, deviate from reality. Let's consider some typical examples. This is what the logo of Volkswagen, the German automotive conglomerate, looks like. And here's how thousands of people remember this logo. Monopoly Man and his monocle. The Monopoly character wearing a top hat sports a monocle, but in fact, he doesn't. Jif, not Jiffy. People swear that there was a Jiffy peanut butter back in the day, but we speculate they're combining Jif with its competitor, Skippy, Pikachu's tail. Though many of us clearly remember black detailing on the Pokemon character's tail, in reality, it's just yellow. C-3PO has a silver leg. Even the biggest Star Wars fans get it wrong. The robot isn't all gold. He has one silver piece on his right leg. There are quite a few examples like this. The sheer number of people with identical false beliefs led proponents of the simulation hypothesis to tentatively propose that these might suggest the glitches in the software running our virtual universe. Of course, these assumptions may seem to lean heavily towards the realm of popular science fiction, but the wide incidence of the Mandela Effect still urges us not to discard it entirely. Where did the idea that we are living in a simulation come from? And why do some people believe it is possible? The world's first truly working programmable computer, the ENIAC, performed about 5,000 operations per second in the 1940s. Today's fastest computer is the Frontier HPE Cray EX235. It computes at a speed of just over 1 exaflops. Here's what that number looks like. 1 quintillion operations per second. That is, today's most powerful computer is more powerful than the first one by a factor of 200 trillion. And it's been less than a century. If things continue moving at the same pace, then what? Even simple logic suggests that in the future, we'll be able to simulate entire universes. But if such a possibility exists, who knows? Maybe it's already happened. In 2003, Swedish philosopher and Oxford University professor Nick Bostrom published a serious scientific work with a simple and a little frightening title, Simulation Argument. We will try to explain in a simple way what the authoritative and globally recognized scientists came up with. So Nick Bostrom has 5 assumptions, and if all of them are true, then you, dear viewer, are probably living in a simulation. The first assumption: it is possible to simulate consciousness. This is a very important point, As you have noticed, all this time we have been skirting around the issue of consciousness. Let's suppose we've created a super complex simulation with exactly the same people as us running around. These bots, these NPCs, are also so sophisticated, let's say that they're capable of wondering if they're in the simulation. But wait, how can they think about anything? They're soulless programs. After all, you wouldn't think your smartphone could think or feel anything, would you? And it's much more real than a simulated character in a video game. In fact, this is too quick an assertion. Modern science defines consciousness, in brief, as the property of a complex system to reflect reality. That is, if something is complex enough, very, very complex, then it can have consciousness. And again, that's very briefly and simplistically. And we know such a highly complex system, the human brain. We know for sure, 100%, that this piece of organic matter can be a carrier of consciousness. But the brain is made up of just the same molecules and atoms that make up everything around us. Complex electrochemical reactions take place in it, and that's what we call thinking. But wait a minute, doesn't something very, very similar happen in modern computers? Do you see what this is about? We have not the slightest reason to believe that consciousness can appear only and exclusively in a jelly-like piece of organic matter. And if some microprocessor system would be endowed with the same complexity, there is not a single law of physics known to us that would deny the emergence of consciousness in such a system, or even more than one. That is, the conditional characters in a super mega complex simulation of the future may be as complex as the human brain, and there is no reason to believe that they could not develop some resemblance to our consciousness. Of course, that would require some enormous computational power. Gigantic. But recall the beginning of this video. How many times has the power of computers grown in just 80 years? 200 trillion times. And what if progress continues for another 80 years? Or 80,000, or 80 million. And here we come very close to Nick Bostrom's second assumption. The second assumption: the technological progress will not slow down in the foreseeable future. It's pretty clear. We assume that humanity will not hit an insurmountable barrier in its progress. Quite recently, such a barrier has loomed on the horizon, and futurologists got a bit discouraged. You've probably heard of Moore's Law. If you have not, let us summarize it briefly. It is not even a law, but an assumption based on observations formulated by Intel co-founder Gordon Moore. It states that the computational power of computers doubles about every 2 years. And it did happen that way with slight variations for decades. However, at a certain point, the law stopped working. The direct proportionality of Moore's Law began to decrease. Physical and technological limitations began to affect further growth of computational power. This trend became noticeable already in the early 2000s. Decreasing transistor sizes due to extreme limits, physical limitations in signal transmission, and increasing power consumption hindered further strict compliance with Moore's Law. Designing and manufacturing more powerful processors with high transistor densities became increasingly difficult and expensive. That's why futurologists became so despondent, and skeptics started talking about the very capacity limit that would be physically impossible to overcome. However, companies began to look for alternative ways to increase computational power, such as multi-core processors, optimization of algorithms, and development of specialized hardware solutions for specific tasks. Now, we are at an epochal turning point, when quantum computers are no longer a theory, but a reality. It is only a matter of their mass production and reduction of production cost. And quantum computers are not even something more powerful, but something fundamentally different. The physics working there is completely different. Who knows what else we will invent in a few generations, when quantum computers will become an ordinary thing? So we can be pretty sure that Nick Bostrom's assumption that computational power will not decrease is quite reasonable and justified. Okay, then what about the third assumption? The third assumption: advanced civilizations do not destroy themselves. Really, why should we care about technologies of the future if we simply will not get to this future because we will just die out? We will kill ourselves in a nuclear war or perish because of an asteroid impact, not being able to protect ourselves from it or settle on other planets. Well, it's even simpler here. If we put aside the elusive idea of the Great Filter, it is easy to understand that if we do manage to resettle on other planets, human civilization has all chances to become immortal. And as you know, Elon Musk, with his mission to Mars, is deliberately trying to help us do that. And he's making notable progress. One man, so far. We sincerely wish him luck. Let's move on. The fourth assumption: advanced civilizations want to run simulations. Indeed, as long as we ourselves are not such an advanced civilization, it is quite difficult for us to imagine why those advanced ones, would want to do this. Nick Bostrom has suggested that one reason might be historical simulation. People from an advanced civilization might want to see what their ancestors did, but instead of reading books, they play scenarios. Or we might be characters in a very advanced video game or something else. Who knows what those advanced ones might have in mind? After all, let's look at ourselves. The more we develop, the more we play video games and wander around the meta-universes. Why would this trend start to fade? Finally, the fifth assumption: if there are a lot of simulations, there's a good chance you're part of one of them. Well, that's it. Here we go. All 5 assumptions are working. There is no reason to disprove any of them. Are you getting a little uneasy? Here is what American astrophysicist and famous popularizer of science Neil deGrasse Tyson says about it. According to him, admitting the idea that it is possible to create a simulation within a simulation automatically means that we are likely to be in one of them. We take the computational power available to us today and realize that we have the ability to create an entire world in a computer. Now imagine a future where the power will be even greater and you can create characters who have free will. You set the laws by which this world lives. Now imagine that you are a character in this game. You think you have free will, and you decide that you want to invent the computer. And you do. Then you decide to create a world in your computer. You end up with a multitude of universes before you. You throw a dart. Which universe are you most likely to hit? The first universe? The real one, where it all began? Or the countless simulations that came after?
You look at our computing power today, and you say, I have the power to program a world inside of a computer. Well, imagine in the future where you have even more power than that, and you can create characters that have, for example, free will, or their own perception of free will. So this is a world, and I program in the laws that govern that world. That world will have its own laws of physics and chemistry and biology. Now you're a character in that world and you think you have free will, and you say, I want to invent a computer, so you do. Hey, I want to create a world in my computer. And then that world creates a world in its computer. And then you have simulations all the way down. So now you lay out all these universes and throw a dart. Which of these universes are you most likely to hit? The original one that started it, or the countless simulations, the daughter simulations that unfolded thereafter?
Elon Musk even goes much further and exaggerates it a bit. He says, we'd better hope we're in a simulation. We either create simulations indistinguishable from reality, or civilization will cease to exist. Those are our options. Elon believes that we are hardly living in a basic, real reality. Discussion of the simulation hypothesis sooner or later leads to the fact that statistically, it is really unlikely. Nick Bostrom is also certain. The chance that we are living in a simulation is very high. Meanwhile, Neil deGrasse Tyson reflects as follows, refining his earlier conclusions. If we haven't yet reached the technological stage of development to create our own realistic simulations, then either we're living in a main reality or we're living in the last simulated reality in the chain. This means the chances are 50-50. We're still on Musk's side, though. Of course, we've outlined things very simplistically here. In fact, it's much more complicated than that. The difficulty of finding a definite answer to the question of whether we are living in a simulation was outlined by philosopher David Chalmers. Any evidence in favor of a particular theory can be artificially simulated. That is, the hypothetical creators of our simulation can deliberately lead us down the path they want us to go.